I'm Mohamed Bahnasawi, or Mohamed Abu Lala. I'm from Cairo, Egypt, and I'm working at Siemens EDA in Caliber QA team. This is our agenda today. I will talk about a brief biography for the paper authors. Then there is an introduction for integrated circuit IC industry, and what is the effect of using EDA tools in this industry. And there is no choice for the EDA or the quality of an EDA. It's must. After that, I will go through the risk-based testing approach with more details for each stage. Then I will go through a brief for the tested tools as a case study for applying the RBT or risk-based testing on it. Then there are some results for applying RBT for these tools, and finally there is a conclusion. The biography, the first author is me. I am working as a senior software QA engineer with an experience of 5 years till now. Ahmed Khater is a QA team lead with around 14 years of experience in software development and testing process. And finally, Reem is around 25 or more than 25 years of experience in software testing and software development. Now we are going through the integrated circuit industry and what is the integrated circuit industry. This industry started with the invention of the first transistor, which was built in 1947 by John Bardeen and Walter Brattain. Both of them are working in Bell Labs. After that, in 1959, Bell Labs invented the most famous transistor in this industry, which is the MOSFET transistor. And this transistor is the dominant one in use in the industry until 2020. As an info, Bell Labs is the research arm of AT&T, and now it's part of Nokia. After that, there is a huge growth in this industry. As in around 10 years, there are many circuits or complex circuits were introduced in this industry. First, there are some circuits contains around 10 gates. Each gate is around 4 or 6 transistors. This scale is named of small scale integration circuit, SSI. After that, the complexity increased, and there is a next level of complexity, which is medium scale integrated circuit, which is containing around 1K of gates. After that, the next level of the complexity, which is large scale integrated circuit, which contains around 10K of gates. This level is introduced in 1970 by Intel. This processor is, which his name is 4004. It was a 4-bit microprocessor, and it was compatible with 256-bit memory, bit, not mega or kilobit, just the bit memory. Now, or through this growth, one of co-founders of Intel, which his name is Moore, was introduced it's not a law, it's an observation, which is the number of transistors in this industry will be doubled every 18 months or 2 years. As you can see, the Intel processor, which is 4004, it was around 10K of transistors. Now we have some processors in Apple, which is Apple 30 or Apple 12, Apple 13 or Apple 12. Some processors from AMD or some products from NVIDIA. They are around 50 billion of transistors, and this was in 2020. To do this growth in the industry, or doing this law by doubling number of transistors in the circuit, it can be done by increasing the size of the circuit, or reducing the size of the transistor to make the circuit containing more transistors or multiple number of transistors. To reduce the size of the transistor, this process name is getting the new technology nodes. Technology node for the processor of Intel 4004 was 10 micrometer. In 1994, the technology node was 350 nanometer. Now, many fabs are now working in the technology node of 3 nanometers. And there are many research papers to generate the technology node of 2 nanometers. The atom of the silicon, which is the base of most of our the base of the transistor, is around half of this value. So we are so close for the base of this industry. So this growth was not be accomplished without any some sort of automation or tools to do something like that. EDA. First, what is the meaning of the EDA? EDA is the electronic design automation. These tools are developed to reduce the complexity of the process of the designing IC circuits. Before EDA, the process of the IC design was by drawing layers by hand, checking the layers by magnifying glasses and eyes. So the bugs was very near to us to be found, as it's a human activity. As a funny joke, one of the first Intel products, which is 3101, this was developed to be dealing with 64-bit RAM. It was actually fabricated as a 63-bit RAM, as there is a wire neglected through cutting the wire of designing the circuit. Through the process of IC design, there are 5 main phases. Without going through each of them, I will talk about physical verification and about process. This process were accomplished by just in 2002 by doing these 3 checks. In 2019, we are doing this step by doing all of these checks. So the need of the EDA became higher to satisfy the needs of our customers. In the fab side, IC fabrication is depending mainly on the crossing light through masks, which is about some holes, and there is an phenomena in physics, which is crossing light through any hole. There is a light diffraction will be done if the hole size is lower than the wavelength, which is 130 micrometer. As you can see, we are working in nanometers. So there are a lot of light diffraction through the IC process. So we are using EDA to enhance the resolution by if this is the shape of the mask, the IC fabrication process will do something like that, and this is not correct. So by using some tools like OBC, we are change the shapes of it, be something like that, to get the correct shapes which we are in need. As you can see, we are dealing with many of equations in physics, and there are values of nanometers, and all of that need more quality to achieve. And the faults in hardware are very cost is very high, as there is an incident which is the Pentium processor by Intel. There is a fault through designing the floating point division unit. This fault costs Intel in 1995 about $475 million, which is equivalent to $752 million in 2020. So any fault in hardware costs the customer too much of $1 million. And as the industry of IC is lending mainly on EDA tools, so the quality in EDA is not a choice; it's a must. And there is another problem in EDA, which is we need to balance between the requests of supporting new technology nodes to get more customers and to keep the old customers by providing him the help to in their marathon. Also, we need to introduce new capabilities or features. This is the second arm of our balance, is introducing more features and capabilities to the tool to be more powerful. All of that should be done with high quality and in a tough deadlines. So we are in need in EDA to introduce or to use more powerful testing strategies or approaches to prioritizing efforts and allocating resources. The best choice for that is the RBT or the risk-based testing, as it's mainly prioritizing risks of the tested tool, and after that we can allocate our resources and so on. All of that will be done without affecting the quality of the tested tools. Now we are going through the risk-based testing approach. This approach is mainly contains or built on 5 main stages: identification of the risks, after that assessment, mitigation, monitoring, reporting. Monitoring and reporting are most important 2 stages in this approach, as they act as feedback to the stakeholders and the cross-functional team to how much the testing strategy was powerful through the testing process. We will go through an example for each stage. First, for the risk assessment, the QA person or QA team will identify the risks in the tool. The risks can be due to the complexity of the flow, lack of experience of the developer. It also can be how much is this part of the tool dealing with a legacy code or a buggy code. All of that can be act as a risk. After identifying the risks, there is the stage of risk assessment. The risk assessment is mainly about give scores to two factors, likelihood and impact. Likelihood and impact is the likelihood factor. It's for the code wise, and the impact factor it was for the customer wise. So through the meeting of the stakeholders, the likelihood can be determined by the software complexity, potential defect locations, how is this part of the code is legacy or buggy or something like that, and this info will be determined by the R&D person. For the impact factor can be determined by the customer wise. How much this part of the code is critically to the user? Is there any workarounds for this flow or not? How much this scenario reliance for or how much is important for the customer? In this paper, we introduced just the grid of 3 by 3, so we can give scores of 1 or 2 or 3, just that. Some papers are assessing the risks by 4 by 4 or 5 by 5 grid, but it's up to you. It's depending mainly on the application you are testing. But our choice is just for the 3 by 3 grid. Here in the risk assessment, through the meeting with the stakeholders, each team member give a score for the impact and likelihood. The priority is the result of multiplying these two scores. After that, we solve these scenarios, and the first one will be the critical scenarios, which should be applied first in through testing process. After that, the high scenarios, then medium, and after that the low scenarios, or the scenarios with a low risk. The risk mitigation is the process of designing these risks and implementing them, and the process of execution or automating these test cases and so on. For the risk monitoring and reporting, as I said before, this process is very important. We always review the progress of the plan through this process. Efficient communication between the cross-functional team is very important, as we may need to choose to change the testing strategy through the testing process. We have 4 testing strategies in testing. First one is risk reduction, by going through the testing and reduce the testing, or reduce the risk of this, reducing the risk of this feature and so on. The second one is risk avoidance, by protecting or not going through the deal for this feature and avoid any engage for this feature, as it may be very important to the customer, and it's a low quality, so we will avoid going through that. Risk transfer, which is accomplished by using an outsource resource, by using a third party or a company or person to test this feature. And finally, risk acceptance, which is it's okay, we are going with this level of quality for this part of the tool, and there is no issue to go live with this level of quality. For EDA, the third one, it's not easy to be chosen, as as we need the experience in this field, and it's not easy to find anyone with this experience in electronics or EDA and so on. Now we are going through a brief for the tested tools. Actually, my team is working for developing tools to introduce random layout for designers. It's necessary to doing this activity for many fabs or many customers to test their fabrication machines or their DRC kits before using them before using these kits on a realistic layouts. The first tool, which is CRA, tends to create random cell array. This tool is just creating a random placement for the standard cells like that. We give it these standard cells, and it generates a random placement for these cells. This activity will be done according to many rules and many steps of rules which the designer will be provided through using this tool. Or via VRB, via random placement. The VIA is one of the most important parts in the layout. It acts as a bridge or as a layout or any integrated circuit built by levels. So sometimes we need to pass a signal over some wire. So by using VIA, we will get it in a higher level or a lower level, and move this signal through this level and get back to the initial one, and so on. So it's one of the most important parts in the layout. So many of our customers need something of these tools to generate random placement of VIAs by a specific criteria to test their kits on it. By applying risk-based testing on these tools, CRA, the risk identification is identified 36 risks. 15 of them are in critical level, 6 in high, 11 in medium level, and finally 4 in low level. As you can see, the 15 risks in the critical level, there are 4 as a functional risk, 5 in the integration risk, 3 CR performance, and 3 is negative. We are always using or start our testing as a functional testing and integration testing, and the performance will be the last step of the testing, as we always focus on the functional and integration. The performance is the last step in our testing. Now we are doing some performance testing in very early stage in testing process. The time planning for testing CRA is around 1 hour for risk identification, 30 minutes for risk assessment, the meeting which was scheduled between the cross-functional team to assess the identified risks. There is a 1 working day for preparing the environment and creating the tested data and so on. There is around 50 to 70 minutes to test each scenario, and finally the total time for testing CRA was around 5 working days. Through testing, the overhead time for the RBT is around 4%. So it's not a big deal to use RBT, as the overhead is just 4%. During the critical risks, there is about 5 critical bugs, and all of them were discovered in very early stage. So the R&D team have a great choice to fix them as early as possible before the release cycle. After that, there are some lower priority features received partial testing. So the cross-functional team prefer to protect these scenarios. So through the reporting phase of RBT, the cross-functional team prefer to change the testing strategy to be avoid the deal for these features. Finally, as I said before, performance testing started in very early stage, as it was important to this customer. Regarding the VRD or the VIA replacement tool, the critical there were there is around 13 critical risks, nine high risks, and 1 medium risk, and there is 5 low risks. The risk identification took about 1 hour to be done. The risk assessment is around 20 minutes. The total time of testing is around 3 working days. The overhead in this case study was around 6% of the total time. During the risk identification process, there is a scenario which is not stated well in the requirement document and functional specification. It's a bug, and we identified it in very early stage. It seems there is no benefit for applying RBT in this case, but actually, as the old school testing techniques also will define this bug in early stage through reviewing the requirement document and functional specs. But actually, using RBT measures the satisfaction of the team, as we always cover the most critical scenarios in the first steps in the testing process. So it was the chance to modify or reallocate our resources by getting a testing resource to test another tool, as there is a satisfaction to this tool as it was a high quality one. And finally, for the conclusion, RBT focus on the flows, which is always fail or it's buggy flows, and it's important to the customer. RBT allows stakeholders to make early decisions for the testing process, and this shortening their time to the market. The overhead of using RBT is around 4 to 6% of the total time of the testing. Instead of using old techniques, which makes the performance in the last steps in the testing process, now performance and negative can be done in the early stage. And finally, the order of testing became depending on the customer need, not as we always do by doing functional integration, then test, then performance, and so on. Thank you.